So, if you're a software engineer or cloud architect, you probably remember exactly where you were on August 17th, right? The day your deployment pipelines just stopped. Today, we're doing an explainer on that massive 8-hour GitHub outage that basically sent shockwaves through enterprise dev teams everywhere. Oh, and a quick heads up before we dive in. While the summary for this explainer was put together using Gemini Notebook, every single detail we're talking about is strictly sourced from actual public data. We're talking GitHub's official root cause analysis and their status pages. No rumors, just the facts.
We've got a lot of ground to cover today. We'll breeze through the SLA failure, break down the actual timeline of the outage, trace the cascading root cause deep inside the architecture, look at how Copilot accidentally created a massive retry storm, check out GitHub's fixes, and finally, discuss how to protect your own CI/CD pipelines. Let's get right to it.
All right, jumping right into Section 1, the 3.9's SLA failure. We really need to talk about the huge reliability gap this incident exposed across the platform. Okay, so this perfectly illustrates the two-tier reality GitHub is dealing with right now. On one hand, foundational Git operations, your basic push, pull, clone, they are rock solid. We're talking a 99.99% 90-day uptime. That is essentially carrier-grade reliability. But then there's GitHub Actions. Actions is the absolute backbone of modern CI/CD, but its uptime plummeted to 99.33%. Over 3 months, that translates to roughly 14 and a half hours of accumulated downtime. Seriously, think about that. That's 14.5 hours where engineering teams literally couldn't ship features, run tests, or push critical hotfixes. To put that into perspective for the business side, a standard 3.9 service level agreement, or 99.9% uptime, gives the cloud provider about 8.7 hours of allowable downtime for an entire year. Well, this single August 17th outage lasted nearly 8 hours on its own. So they basically blew almost an entire year's downtime budget in one single afternoon. If you're leading an engineering org, you really have to start asking yourself, is putting all our eggs in the GitHub Actions basket becoming a serious business risk? Moving to Section 2, Anatomy of the August outage. Let's look at the timeline and see how this thing actually spread. Keep in mind, this wasn't an instant blackout where somebody just tripped over a server power cord. It was a slow burn. Over a span of roughly 100 minutes, things just fell like dominoes. GitHub first confirmed the outage at 9:40 a.m. Eastern Time. By 10:04 a.m., archive download errors started spiking. By 10:31, GitHub Copilot gets pulled down into the mess. And believe it or not, it wasn't until 5:15 p.m. Eastern that they finally confirmed a full resolution. Now, here's a really crucial, kind of sneaky point during that opening window. 50% of raw content paths failed. Think about all the hidden dependencies relying on those paths. Docker builds, Go module fetches, package manager installs pulling directly from GitHub. So for most of the working day, half of all automated build jobs were just failing silently right in the middle of their runs. You know, engineers were pulling their hair out trying to debug their pipelines because the errors didn't immediately look like a platform-wide GitHub outage. All right, Section 3, Tracing the Cascading Root Cause. Let's open up the hood and diagnose the exact failure path inside their central US data center. This right here is the textbook anatomy of a cascading failure. Step 1. It all started when a single Istio sidecar pod hit its concurrency limit because of a traffic peak. Normally, no big deal. It should just scale up gracefully. But there was a fatal flaw in the auto-scaling policy. It was watching the host services limits, entirely ignoring the sidecar limits. So the sidecar is literally screaming for help, and the autoscaler is just looking the other way. Because it didn't scale, traffic backed up. Eventually, 4 HA proxy nodes completely exhausted their flow limits, and boom, gateway authentication degrades. The second that auth path fell over, every service relying on it just started crashing. Which brings us to Section 4, Copilot and the retry storm. GitHub tried to shift traffic to mitigate the issue, but that actually triggered something way worse. What's absolutely fascinating about this failure is how client-side software inadvertently weaponized a back-end issue. When traffic shifted to Northern Virginia, delayed responses from a single internal endpoint exposed a latent bug sitting inside VS Code. When VS Code didn't get its Copilot token fast enough, it didn't gracefully back off. No, it entered this highly aggressive, optimistic retry loop. The result was just staggering. The Copilot token service normally runs at a very comfortable baseline of around 7,000 to 9,000 requests per second. During this retry storm, it spiked to an astronomical 100,000 requests per second. 100,000. The client-side retries basically DDoSed their own authentication infrastructure, massively accelerating the exact failure they were trying to bypass. Moving to Section 5, Fixing Architectural Bottlenecks. Let's see how GitHub finally stopped the bleeding and what their long-term remediation looks like. To get things under control, GitHub had to force recovery through some pretty aggressive triage. They temporarily disabled off-token retries and just started blocking inbound Copilot requests right at the load balancers with HTTP 403 errors. They had to forcefully cut off that retry storm to stabilize the core. Beyond that immediate triage, they're now correcting those service mesh autoscaling policies so they watch the right metrics, auditing Istio concurrency limits globally, and, most importantly, continuing this massive migration of critical paths out of their legacy data centers and into Azure. But honestly, the true underlying vulnerability here is architectural. GitHub's core is an aging 2 million-line Ruby on Rails monolith. In a tightly coupled monolith like that, components just don't feel gracefully in isolation. Instead, a highly localized issue, like one ICO sidecar failing to scale, drags everything else down with it. That stress propagates instantly across the shared backbone, taking down PRs, issues, Copilot, and CI/CD all at the exact same time. Finally, Section 6, Protecting Your CI/CD/CI Pipelines. What should we actually take away from this explainer to build true enterprise CI/CD resilience? Here are your actionable takeaways. First off, you simply cannot rely entirely on GitHub raw content URLs for your automated builds. That is a massive supply chain fragility. You have got to cache build dependencies locally or in a controlled artifact registry so your builds can survive a network partition. Second, if you have enterprise availability commitments, you need a fallback CI/CD path. Whether that's GitLab, CircleCI, or just maintaining a warm fleet of self-hosted runners, have a backup. And lastly, don't forget to audit your user account states. If your enterprise SIM provisioning fired during the auth outage, things might be disrupted. So I'll leave you to think about this. If Actions goes down again tomorrow, is your team completely paralyzed, or can you still ship code? It's a critical conversation you need to be having. Thank you so much for joining me for this breakdown. And hey, to catch more deep dives into cloud, security, and AI insights just like this, be sure to subscribe to the YouTube channel @ELSstream. Keep building resilient systems, and I'll see you in the next explainer.